Hello everybody, I'm Jean-Romain. I'm here to present computing delay constraint least cost path for segment routing is easier than you think, which is a joint work between the University of Strasbourg, where I'm currently pursuing my PhD, and Cisco Systems. So there is a lot to unpack from the title alone, so I'll start off with a little bit of context. Alright, so as you know, within the network, packets will usually follow best paths, and these best paths are computed by minimizing a single metric, the IGP cost, which considers the bandwidth usually and some of the ISP's specific needs. However, these paths are not suited for some specific kinds of flows, which have strong requirements across multiple metrics. In this case, you may need to perform traffic engineering, which means that you have to compute specific paths, which have to take other metric into consideration, such as the delay, and then ensure that the flow actually follows the path you computed for it. Now, there are several technologies that allow you to do traffic engineering, but usually they are pretty tedious to deploy and suffer from scalability issues, which hinder the use of traffic engineering at a large scale. However, now there is a new technology, segment routing, which allows to perform traffic engineering easily while remaining scalable. So for those who know, it's a bit like loose source routing, meaning that you take your path, you translate it into a list of checkpoints that you want your packet to go through, and you put this list within the packet itself. And then the routers are going to read this list and forward the packets through each checkpoint sequentially following the best TCMP paths. And these checkpoints are also referred to as segments, basically. There is a slight little trick. Of course, you can't have more than 10 segments or 10 checkpoints in your list. It depends on the hardware. It might be more, it might be less, but it's usually around 10. But beside this, operators now have an easy and a scalable way to perform TE, so everyone should be fairly happy. But of course, it's not the case, or I wouldn't be here presenting this to you. Uh, Now that segment routing allows ISPs to perform traffic engineering at a large scale, they want to put it to good use, of course. So in particular, there is a fairly huge demand regarding the ability to compute more intricate paths. More precisely, for new real-time services, ISP would like to be able to compute paths which can guarantee a certain delay to ensure a high interactivity, and also still minimize the IGP cost, to consider the bandwidths and the network design. The problem is respecting a constraint on an additive metric, so the delay in this case, while minimizing another one, the IGP cost here, is a problem known as DCLC, delay constraint least cost. And this problem is known to be NP hard. So at first it seems pretty impossible to bring strong guarantees regarding this, the execution time of an algorithm solving this. So this is not what we want in a network context. In addition, this is actually where segment routing will come back to stab us in the back, because uh, if we find a path eventually which respect what we want, we need to be sure that it can be encoded in less than 10 segments. So in summary, we would have to find a path which respects a constraint on the delay, minimizes the IGP cost, this is NP hard in itself, and then ensure that this path does not require more than about 10 segments. And another problem is that most solutions to DCLC are heuristics, so we can't use them because they don't bring strong guarantees, and also they don't consider segment routing. But if you don't consider this new constraint brought by segment routing natively, it will actually drastically increase your execution time because you may rely on heavy live conversions, which will boost your complexity by a fair margin. Instead, what we are going to do here is design our algorithm around segment routing to deal with these new constraints efficiently. And on top of this, we are going to look at how real network characteristics simplify the problem for us. And thanks to this, we will be able to create what we named best two-cup, which is a simple, straightforward algorithm which we believe to be the first deployable DCLC scheme able to deal with with DCLC in large segment routing domains in less than a second. So first we have the problem of the NP-hard nature of DCLC, which means that it seems like we can't bring strong guarantees regarding the execution time of our algorithm. And then we also have to deal with this additional constraint brought by segment routing, the number of segments or checkpoints. So we'll deal with each point one by one, but we'll start with the NP-hard nature of DCLC. Okay, so to do so, we need to understand why DCLC is NP-hard to begin with. So you can show this on a small example, the one you can see on the right side of your screen here. On this example, you have several paths from 1 to 3, which differ both in cost and delay. For example, you have A here, which has a high cost but a low delay, and you have other paths, B and C, which have a better cost but a worse delay. But you can notice that there is no best path per se, right? They are all better on at least one metric compared to the other two. They are called non-dominated paths, and they form what is called the Pareto front of the solution. So you may think, yes, but we ultimately want the least cost path, so we want C. But it's only true for node A, right? We would like to consider all destination, and maybe we aren't done with the exploration of the network yet. Maybe there is a node after this, node 4, and out of all of these paths, A, B, and C, we can't actually predict which one will be the DCLC path for node 4, because the one of lowest cost may actually exceed delay when we extend it, the delay constraints once we extend it. So we have to remember and explore all the paths within the Pareto front. The problem is here the Pareto front is small and cute, but it may be very large with a lot of paths. It may actually grow exponentially when you explore the network, which is why DCLC is considered to be intractable and NP hard. But there is something to consider. It's that if the metrics are bounded and discrete, the Pareto front will not really look like this, but more like this, right? Because there is only a few possible values, and they are bounded, so it can't exceed a certain threshold. And when you consider this, well, DCLC is not NP hard anymore because there is a constant number of possible values for the metrics. So why am I bothering telling you this? Well, it's because we argue that when you consider DCLC for real ISPs, uh, at least one metric will always be strongly bounded and discrete and thus reduce drastically the size of the Pareto front in a predictable fashion. So the IGP cost ultimately, of course, depends on the configuration. So let's focus on the delay. First, well, we know that it will be strongly bounded because we want a high interactivity, right? So there is a strict bound on the delay. The fact that it's discrete is a bit more tricky to explain because the delay is usually represented with a very high precision in memory. So you could say that we have so many different values, it's almost continuous. But if you take the accuracy of the measurements into account, you realize that most of these delays do not have a large enough difference to actually be able to discriminate the paths. You can only say that they have about the same delay, which means you can actually discretize the delay without losing any relevant discriminating information. And for each of these discretized intervals, you can then discriminate the paths which have the same approximated delay thanks to the cost. And thanks to this discretization that we just did, you will only have one path per delay interval within the bound. We refer to this number of paths as gamma. And as I said, gamma will be the number of paths you have to deal with when dealing with DCLC in an ISP. Meaning that ultimately, DCLC is actually polynomial in gamma. You can, of course, tune the size of the intervals, right? But as long as the intervals are smaller than the accuracy of the measurement of the delay, you will technically remain exact. Okay, so I'll bring back my face because we actually did something pretty cool here. We dealt with the NP hard nature of DCLC by considering the inaccuracy of the delay measurements, which allowed us to discretize the metric, the delay metric, and then allowed us to reduce the Pareto front to a predictable size, gamma, and thus made DCLC polynomial in gamma. So that's the NP-hard nature of DCLC dealt with, and we can now move on to the other challenge, which was the additional constraint brought by segment routing, meaning the number of segments. Okay, so to do so, I guess a more thorough explanation of segment routing is in order. So as I said in the introduction, with segment routing, you can specify the path you want your packet to follow by translating it into a sequence of checkpoints or segments. And you can ask for your packet to go through a specific node by using a node segment, or through a specific link by using an adjacency segment. By doing this, you can make your packet follow known shortest path. For example, here the shortest path from 1 to 4 is the one displayed, but say that for some reason I want it to go like this. I can break this path up in several checkpoints I want my packet to go through. So here, first I want my packet to go to node 2, of course. So I can use a node segment to specify this. Once it's on node 2, I want it to go specifically through adjacency A, so I can use an adjacency segment to specify this. And once it's on node 3, I want it to go to 4 through any of the best ECMP path available, so I can just use a node segment to specify this again. And once I've done this list of segments, I'm pretty much, well, done. I just need to put this on top of my packet, and then I can send my packet on its merry way. It will follow the path I specified until it reaches its destination. So the problem was, if you recall, that the number of segments I can stack is limited to about 10, maybe less, maybe more, but around 10. So how can we deal efficiently with this new constraint? Well, we are going to use a structure construct known as an SR graph. Simply put, an SR graph represents the segments as edges. Right? So for example, from node 1, I could use a node segment to get to 4, and my packet will do so by following the best IGP path, which has a cost of 2. So we add an edge from 1 to 4, which represents the node segment, and this edge will have a cost of 2, which is the cost of the path encoded by the node segment. We do this for all nodes, so in the end our SR graph looks like this, where one edge is equal to one node segment. And the weight is equal to the weight of the path it encodes. But here you may have realized that the adjacencies are missing, so I also need to add adjacency segments. For example, once I'm on node 2, I may want to use the adjacency A specifically, which had an IGP cost of 10, so I add this on the graph, and then I'm done. I have an SR graph where all my segments are represented as edges. This construct is actually performed by all routers or sometimes path computation elements once segment routing is enabled. But we had to slightly tune it for our purpose because you may have realized that the delays are missing, which could be a bother when you are trying to solve a problem known as delay constraint least cost. So we just need to adapt this to fit our problem. This is actually pretty straightforward because, well, most of the time, the only thing we have to do is take the delay of the path encoded by the segment, round it to take the accuracy of the measurement into account. Remember that we did this in the previous section to simplify DCLC. So we round it up to take the accuracy into account, and we put it on the SR graph. There are though some subtleties. For example, with ECMP, the packet may go through any of the ECMP path, right? So the only thing we can guarantee is that the delay will not exceed the worst delay out of all the possible ECMP paths. So this is in turn the delay that we are going to use on our SR graph, as you can see here. There is a last little trick. It's that in some cases, some segments from one node to another are worse than any of the other possible segments. For example, here between 3 and 4, there is one segment it has an equal cost, but it's worse on the delay. So there is no point in using a segment which is worse on all metrics than another one. In this case, we can simply remove it, right? We prune a little bit the graph. It will in turn reduce the complexity of our algorithm. So in the end, we're left with this. It's a multimetric SR graph. And what's nice about this construct is that within this, a path of X edges represents actually a path encodable in X segments, right? Because one edge equals one segment. And this is pretty interesting because if we explore this graph in a Bellman-Ford fashion, meaning that we discover paths of X edges at the Xth iteration, it means that There is no point in going further than the 10th iteration, because we know that it's paths that require more than 10 segments, and so they can't be encoded. So thanks to this construct, we can stop the algorithm very quickly at the 10th iteration, and thus we can leverage the constraint added by segment routing by cutting short the execution of our algorithm. So what did we do? We dealt with the NP-hard nature of DCLC by leveraging the inaccuracy of the delay measurements to discretize the metric without losing any important information. In addition, we dealt with the constraint added by segment routing thanks to a specific construct, the SR graph, and to an appropriate path exploration. Thanks to this, we can now design an efficient algorithm, best lookup, which will be able to solve DCLC in any SR domain. Thanks to all of our prior works, the algorithm in itself is actually pretty simple. This is, of course, a further simplified version. A more precise one can be found in the paper. You can also find the code online. The basic idea is, as I said, pretty simple. You start with the only path you know, which is the one to the source. At each iteration, you extend the paths you know by one edge, so one segment. You filter the paths that you found to only keep the one within the Pareto front, right? And the paths that survive this filtering are then extended by one edge at the next iteration. The important thing is that you explore the graph by ensuring that the path you discover at the xth iteration are paths of x edges, and at each iteration you keep only the Pareto front. So thus, at iteration x, all paths of x segments that are on the Pareto front are known. And this is it. You do this segmax time, so about 10 times, segmax being the maximum number of segments you are allowed to use. So basically, during an iteration of this algorithm, you have to consider at most all the nodes you know how to reach, so all the nodes of the graph V. You extend them by to all of their neighbors, which can be V as well. They may have L parallel links between them, and you may have to extend gamma path because it's the maximum number of paths that you can have towards each node, right? And so you have the complexity of our algorithm because you do this segmax times, and it leaves you with the complexity which is displayed at the bottom of your screen. I repeat once again that gamma is tunable, so you can tune it to remain exact so that the intervals the delay intervals are smaller than the accuracy of the delay measurement, or if the problem is too complex, which shouldn't happen on a real ISP networks, you can tune it to at least approximate the solution. This algorithm actually shows pretty good, if not very good, performance. We performed extensive evaluations on both random and real topologies, and we considered a gamma of 1000, which you can see as a delay constraint of 100 milliseconds and an accuracy around the millisecond. On full random topologies, so we put random IGP cost and delays on a double full mesh graph, we never exceed 1 minute, even for 1000 nodes. But even though this is a pretty nice result, given the complexity of the problem, it's actually very far from what Best2Cup is able to do on realistic networks. When we use real topologies with real delays and real IGP costs, we take around 200 milliseconds at most. It's actually for smaller topologies, it's close to 5 or 20 milliseconds, which is admittedly pretty nice performances. Right, so I promise it's the last time you'll have to see my face, but in conclusion, what's this presentation all about? Well, traffic engineering is back with a vengeance, thanks to segment routing, and so ISPs want to be able to compute more intricate paths. In particular, here we aimed to tackle the DCLC problem, which is NP-hard, on top of which segment routing added another constraint. We managed to deal with this by leveraging some network characteristic, especially the inaccuracy of delay measurement, and by using a specific construct that we tuned to fit our problem and an appropriate graph exploration on this construct. By merging these two ideas into an algorithm, we created best2cup, which is an efficient deployable DCLC solution which is able to solve DCLC in large SR domains in under a second. Now there are still some work left to be done. For example, best2cup can be easily parallelized. We could use a more subtle data structure to take advantages of more specific situation, and mainly we are investigating if the area partitioning usually performed by operators could be used to further simplify the problem. Thank you very much for your attention, and I'll be happy to answer your questions if you have any.